I'm John McKenzie. One of the most exciting developments in science today concerns the possibility that it may one day be possible to modify and perhaps even control weather and climate. What this could mean in terms of hurricane and flood control and reduction of damage to property, crops, and livestock would be measured in billions of dollars for the United States alone. The value in terms of human welfare for the entire world defies calculation. During the next few minutes, we'll learn what's being done toward altering clouds to increase rain and to decrease hail and lightning. And we'll also look at some of the research aimed at modifying large-scale weather systems, such as cyclones. Dr. Morris Seamus of New York University talks first with Dr. Roscoe R. Braham, professor of meteorology at the University of Chicago.
Dr. Braham, I'm sure that before one can think of modifying a cloud in any way, he must know something of its properties. How do you characterize a cloud?
Well, natural clouds of the atmosphere consist of dense concentrations of very small water droplets, plus perhaps a few ice crystals and snowflakes in the upper, colder regions of the cloud. We can collect these particles by flying through the clouds with an airplane, and if we examine one of these collections through a microscope, we see something similar to that we have in this photograph. Of course, in a natural cloud, the droplets are much farther apart than they are in this photograph. In an ordinary cloud, there would be of the order of 100 droplets per cubic centimeter.
Not very many.
No, that isn't too many. The smaller droplets would have a size of about 5 microns diameter, whereas the larger ones would be about 50 microns diameter. Contrasted with the cloud droplets, raindrops are very much larger. Here is a sketch of the relative size between a raindrop and typical cloud droplets. It takes between 1 million and 10 million cloud droplets to make a raindrop. And the central problem in cloud physics today is to explain how it's possible for so many cloud droplets to come together to form a raindrop.
Well, how is it thought that they combine to form a raindrop?
Meteorologists who study such problems recognize two basic methods or processes by which raindrops are formed. One of these theorizes that the larger cloud droplets, because they are larger and they fall faster, run into some of the smaller cloud droplets, coalesce with them, and gradually build up in size. This process can be modeled in the laboratory, and we've brought along a tape showing the collision between two cloud droplets. The larger drop falls faster and overtakes the smaller drop, coalesces with it. Continued collisions and coalescences with the very much more numerous cloud droplets would ultimately produce a precipitation particle large enough to survive the fall to the ground as a raindrop.
Now, you mentioned there were two processes. What's the other?
That's right. Now, actually, the second process involves another property of water, which we call supercooling.
What do you mean by that?
Well, supercooling is the state of existing in the liquid form at temperatures well below or beyond the normal freezing temperature. Of course, the freezing point of water is 0 centigrade. But water, when subdivided into particles the size of ordinary cloud particles, may be cooled many degrees below 0 centigrade before it freezes. In fact, natural clouds may supercool as much as 20 degrees centigrade, very commonly. Now, the important point is that the saturation vapor pressure over a supercooled water droplet is substantially larger than that of over an ice crystal at the same temperature. Therefore, if in a supercooled cloud one introduces in some fashion a few ice crystals, then the ice crystals will grow at the expense of the water droplets in the manner we have indicated here on our sketch. Here is an ice crystal in a field of supercooled liquid cloud droplets. The droplets are evaporating, becoming smaller. As the vapor moves toward the ice crystal in turn grows in this way. As it grows, it ultimately becomes large enough to fall through the field of cloud droplets. It may run into some of the cloud droplets, which then freeze upon impact, and we have the condition of riming, producing what we call a snow pellet or a Graupe particle.
These are quite different processes then.
Oh yes, these two processes are quite different, but it is this second process which is involved in most modern cloud seeding experiments. Now, we know that this process can be introduced artificially. Well, the rationale of most modern cloud seeding experiments is that clouds can be changed usefully by introducing ice-forming particles.
You can do this in the laboratory.
It can be done in the laboratory. There are two substances which commonly are used for this purpose.
Yeah.
We use dry ice and silver iodide. Dry ice introduces ice crystals because of its intense cold, and this can be demonstrated in the laboratory in the manner that we show in our film clip. Here we see the trail of ice crystals that has resulted from dropping a pellet of dry ice through a supercooled cloud. The ice crystals grow at the expense of the supercooled water droplets. The growing ice crystals get large enough to twinkle the light, and you see them twinkling there on the screen.
Now, why are these particular substances selected for this?
Well, because we can demonstrate their ability to form ice crystals in supercooled clouds, obviously. The dry ice because of its intense cold. Silver iodide because the lattice structure of the silver iodide crystal is very similar to that of ice.
Now, how do you do the silver iodide
Silver
experiment?
iodide is usually released in the form of a fine smoke produced by burning a silver iodide acetone solution in the manner that we show in our film. Here we see a burner mounted on the wing of a light aeroplane. You notice the burner is lit very much in the manner that it would be used in seeding a supercooled cloud.
Now, how do you apply this to an actual cloud?
The most dramatic and obvious case we can see in our picture here. This is one of the early pictures coming from the cloud seeding experiments. We're looking down on the top of a supercooled stratus cloud. We see a racetrack pattern of ice crystals. This pattern of crystals has resulted from flying an airplane around this track, dropping dry ice pellets. Wherever the dry ice fell through the supercooled cloud, it left behind a trail of ice crystals which grew into snowflakes and fell outward through the base of the cloud.
Was much rain produced in this experiment?
No. A supercooled stratus cloud of this form actually contains very little liquid water, so relatively unimportant amounts of snow would fall from it. However, the process itself has great importance. You see that it has cut a hole in the supercooled stratus. In this region, the visibilities are very much higher than they would be in the cloud itself. And this technique has application for, say, opening airports in the wintertime that may be fog-bound by supercooled fog and stratus. In fact, last winter, one of the commercial airlines used such a technique for landing many flights that could not have landed because of supercooled fog.
What is your feeling about these techniques as far as producing actual rain is concerned?
Well, it seems to me that there's considerable evidence that rain can be increased by the proper application of seeding techniques in certain specific cloud conditions. But generally speaking, we still know so little about the matter of cloud seeding that we just don't have proof beyond a shadow of doubt that you can increase the rainfall when and where you wish. It's a
Might you
problem.
also be able to decrease it in a cloud that's raining?
Oh yes, at least theoretically. If one introduced a very large number of ice particles into the cloud, each of the ice crystals may grow to such a slight extent that they would not fall through the cloud base, and we would have what we call overseeding of the cloud.
I see. Thank you very much, Dr. Graham.